Okay, in this video, I'd like to talk about a topic that you may see now, you may have not used this just in your simple examples so far. When we write simple programs, that's one of the issues we may not worry about. But what is this serialization and deserialization about? I mean, what the words you may easily understand. Actually, this is sometimes this is actually uh, referred to as a SIR, DSIR for short, because the words are kind of long. And this is really just talking about a technique to uh, preserve the state of some of your program state, and either you save it for later when you resume your program, or you may transfer that state to some other program over the wire, and over the network, or maybe another program in your computer. Most of the time we're talking about over the network, that kind of usage. You may also think about this as an issue where you may want to persist the state into a database. Then we're also talking about this serialization, deserialization as well. So in short, we're dealing with data. And when your program runs, it's going to so it's going to have state of your objects. And that is, we're talking about data in your program. So it comes down to the process of serialization is essentially just turn object into stream of bits, and deserialization is just the opposite, to turn stream of bits back into objects. So the objects are basically what you are uh, manipulating with in your program. And imagine these are the objects in memory. Okay. And in the context of C++, so we're talking about, let's say the arrows are pointers, and you have objects that point to each other. And then you may even have a cycle here. You see B, C, E, D, and back to B, that kind of dependency. So then for some reason, let's say you want to save this objects, okay? You want to save it for later retrieval, or maybe, for example, you're playing a game and the user simply stopped playing the game and they want to resume later, right? So you want to save the state of the game, perhaps locally on the file, or send it to the cloud, right? In some server. And so how do you serialize? How do you turn these things into stream of bits? And so later you can turn them back into objects so you can run them again. So that is the SIR DSIR issue we're talking about. There are many serialization formats. Now, when we talk about format, this is really saying what is the mechanism of turning those objects into some kind of representation. How do you represent those objects in this particular format so that you can convert into a stream of bits? What is that stream of bits looking like? So broadly speaking, there's actually two categories of serialization formats. There's textual based, then there's also binary based. Now, really difference is the textual based is human readable. It's designed so that you can actually examine the file and make sense out of it. And the binary formats are, you know, for machines, that they are machine oriented and not meant for humans to read. So you can't really look at the file and make much sense out of that data. So let's look at some of the examples. So textual format. Now, these are the formats that you at least heard of if you have not used so far. So XML. XML is a markup language with this angle brackets with tags. And well, there's actually many related XML um, format. It was for quite some time. It's still today a quite popular format. And for the most part, the XML related, the whole XML family of formats, they are um, standardized. However, there's quite a bit of criticism of XML because the verbosity of the textual format. So, so then someone came along to say, well, let's simplify this a little bit so that, became JSON. And JSON is, yes, it's much more compact and it's still very much readable with with the curly braces and double quotes. That's kind of mostly what you see. And it's hierarchical still. So JSON became very popular mostly because this is the format chosen by JavaScript language. So JavaScript has a native support of JSON to represent data objects. And then, so JSON is super popular basically in the whole web front end community. And that's mostly when you run programs in a browser that deal with a lot of JSON. That's sort of de facto, serialization format for that. Now, you don't have to use JSON, but that's kind of the default choice there. And then there's also YAML. Now, YAML is another type of a serialization format that is so far mostly used for configuration. JSON, XML, they are used for APIs. Like for programs communicating with each other over the network, and YAML not so much for APIs because it's kind of has a very much a human oriented because it's kind of it formats your data hierarchically based on tabs and or spaces. So it's pretty suitable for, again, so limited usage so far. Mostly you see them for configuring your programs. Of course, there's a lot of configuration also really in JSON. That's also pretty popular. And XML, you see a lot of configuration files in XML format as well. Like for example, your Visual Studio, you see the project files, right? They are in XML. And JSON, for example, the Visual Studio Code, which is the lightweight IDE that's very extensible, that uses a lot of JSON for configuring multiple parts of the IDE or your program, how your preferences. Now, YAML is sort of a less used, but it's still also quite popular in certain parts of the programming community. So that's just another textual format that kind of covers some of the most popular. I would say there are the most popular textual format for serialization. And then there's binary formats. So of course there are more performance oriented that are designed for, program to program kind of consumption and not meant for humans to read directly. And so they optimize for, you know, the, 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 the number of bytes it's going to use to represent the data. and also the efficiency. Protocol buffers, it was originally developed by Google, and then it was open sourced and became very widely used. And this is a binary serialization format that is used cross-language. There's a support for most of the popular language that you're familiar with that has a protocol buffer support. And the way the protocol buffer works is that you write a sort of a protocol file it's called the interface definition language. In that particular format, and then that describes the sort of the objects, the fields, and the types of the data. Much like defining the member variables of your classes. And then you compile that file into a target language library, and then you use that in your program. So you can share that, the protocol, the proto file, the sort of the intermediate specification. So you can call that the spec, the object format spec with your consumers, and then they can generate a language-based library. So this language neutral in a sense that you can interchange, exchange messages that between programs that use different languages. And then Java has this thing called object serialization that's built into the language. It's a optional optional way for Java programs to serialize the objects. And then in Python, you got Pickle. So that also is a binary object serialization format. So what about C++? So C++, the language doesn't really provide you a serialization mechanism. But you can use Boost. Boost has this serialization library that is very well designed. Actually, I'm going to show you an example in using Boost serialization. And this module actually supports both textual and binary formats, if you're so inclined. And this is, it's a fine library, and you'll see this in action. And then if you're really interested in seeing more, and these are by no means the complete list. This is like, I just kind of mentioned a couple of popular ones, and also some of the language specific serialization formats. There's actually a lot more. And so of course, when you design software, one of the considerations you have to make is decide what kind of serialization format you're going to use to persist the state of your program or transmit that state over the wire to communicate with other programs. So let's look at this example and Boost serialization. And so, by the way, I'm going to share also a link to a video that somebody else is going to talk about JSON versus protobuf or protocol buffers. And that gives you a little bit more introductory material. You can look at that. So for now, let's look at the Boost serialization library. So what I have here, this is the application is it's a simple sort of a bus schedule kind of a application. Yeah, this is so I'm gonna make this diagram a little bigger. This is the class diagram. So I drew this with Planet UML. So you can open up with the Planet UML extension in your Visual Studio or Visual Studio Code. So when you do OOP, one of the things you really want to learn to do is to draw class diagrams at least. There's many other diagrams you can draw. UML is a very nice standard, and that UML that can be worth its own class to teach. But you can just pick up pieces of UML over time, and one of the first things you should consider learning is this class diagram. So I'm going to keep using a couple more class diagrams. Hopefully you can pick up on those things as you go. And I have also shared the source code of these things, and you'll see it's fairly easy. But you have to understand the meaning of the symbols and use them properly. So, so I'm gonna get back to the serializable just a bit later. And so let's talk about let's look at the class hierarchies. So in this bus schedule domain, we have a class called the bus schedule, and the bus schedule has a a member variable called the schedule. And this schedule is simply a vector of a pair of objects. So the pair of objects, this is for demonstration. So typically, if you design a proper OOP program, you know, unless for quick prototyping, you may just end up using a pair, but pair doesn't give you much of a meaning. You may consider making a simple class or a struct. This maybe we'll call this like an entry, you know, a schedule entry, something like that. So essentially this has two fields or two variables. So here we're just using this standard pair, right? This class allows you to put two variables together, two objects into one. So that's kind of what a pair will do. So here we are holding on to sort of a vector of pairs of trip info and a shared bus route. Now, so I've adopted this sort of a naming terminology, shared. That really means it's a shared pointer, okay? So this here is essentially a type alias of shared, it's a shared pointer to bus route. So bus route, so there's a relationship here. This is the aggregation relationship. So recall our last lecture, aggregation versus composition. And this is a composition relationship here on the left-hand side with the trip info. You may also notice that trip info is defined as a subclass. It's a nested class inside a bus schedule, which has three member variables here for the trip info. Now we have a driver's name. We have the specific hour and the minute for that trip. So that represents the time. So the time the bus, you know, essentially the time the bus starts from the beginning of that trip. And then here's the driver. Okay, so it's just a simple application that kind of just gets this, you know, we're using this domain to talk about this serialization issue. So of course, if you're really designing, like for example, a bus scheduling app, you know, you're gonna end up using some of those objects, of course. So perhaps you have more information you need to hold, and maybe more objects you're dealing with. But this is a simple example here. And so a bus schedule, you know, for each bus schedule, you may have 0 or more, you know, sort of trip info. Because here we're holding on to a vector of those. So and again, a trip info has to belong to a bus schedule. So this is a, and because of the composition, this is sort of the life cycle of this trip info is managed by a bus schedule object. So if a bus schedule goes away, this is destroyed as well. Okay, so difference between the composition and the aggregation. So it uses the bus route. Now bus route is you know, aggregated with schedule. So this is referenced the matching every trip info with a particular bus route. Now, of course, a bus route could be shared, among multiple schedules, if you will, right? Now, what is a bus route? A bus route here, simply we're defining this as a collection of stops, okay? Just many stops, that's kind of the bus route. So here is a vector of a shared bus stop. And again, shared, that means the shared pointer to bus stop type. And I'll get to the talking about the functions a little bit. Let's kind of just talk about the data. And so the bus route is, a collection of stops. And what's the relationship with the bus stop? Of course, here, this is a simply aggregation relationship. The bus stops could exist independent of a bus route. So bus route does not manage the lifecycle of bus stop objects. Now, the bus stop is polymorphic, right? We'll talk about polymorphism. So this bus stop is a polymorphic in the sense that this is an abstract class. Now, if you look at this symbol here, this is the stereotype of this class. It's an abstract class. How, what makes a class an abstract class, right? If you recall, it has at least one pure virtual function. So that means that function has to be implemented by the derived classes. And so as now here you see this is actually private, and now as you also recall, the accessibility and the overrideability are some unrelated, right? So you can still override them, the private virtual functions. Okay. So there are two kinds of bus stops here with, in this particular application. There's bus stop that's at a corner, at an intersection between two streets. And then we may have a bus stop that's at a point of interest or some kind of building, right? That's a destination. And so these two are concrete classes. They are realizing this relationship here with a dotted line with a empty triangle arrow here. That is a realization relationship versus the solid line. If you see a solid line, that's basically a generalization. That's the inheritance is a relationship. Is here decided to use a realization because this implements sort of this abstract class. This is required to be implemented. So if we could, is an abstract class, and that kind of I think is more appropriate to use the realization relationship here. And so, yeah, so the corner has two additional fields, two additional variables to the street names of two that makes up a corner, and then this destination has just one name for that destination. Now the bus stop itself, that base class, has two variables. That's the longitude and latitude. That basically specifies the location, the exact location of that bus stop. And so it uses these two member variables. And so there's also a GPS position class that records the degrees, minutes, and seconds of the GPS location. Well, not the GPS location, the longitude or latitude in terms of the degrees and the minutes and seconds. Okay, so this longitude and latitude makes up the location in GPS system. All right. So now there is one more thing. It's called a serializable. Now serializable has a here indicated there's a function called a serialize with the parameters omitted here. Now, serializable is not a class or interface or anything. And I call this a concept because in order for those classes to be serializable, in the sense that that we can actually serialize them into uh, a stream of bits, right? To save that state somewhere, and or maybe transfer it over, or maybe put it in a file, whatever you want to do with that serialized data. So they need to implement a function called serialize, and they don't have to derive from like a interface called serializable. So but then this becomes it's a constraint on those classes for them to be able to work at compile time, to be able to say you can actually serialize, but they have to implement a function called serialize. Okay. And so this is essentially just is a concept in C++20, although the Boost library is not really making this into a concept. But this really comes down to is a concept. It places constraints on your classes that in order for that to work with the Boost serialization library. So here I have all these classes that we want to serialize. They are realizing this uh, concept. So they all have this serialize function defined. All right. So that's really what the whole program structure looks like. And so this makes it very clear and easy to reason about. Now, a couple of functions. By the way, if you see red color means private. If you see green, that's public, right? If you haven't explained that. Now, the bus schedule has a public function called append with a bunch of information, driver, hour, minute. Actually, this information, as you can see, this is what we can fill up at trip info. But the consumer of this class does not need to be aware of trip info. In fact, trip info is a private class inside bus schedule. And so they pass in this information. So internally, it's going to make a trip info object out of these three parameters, and then also we take a shared bus route. And so we can put that pair of information into that vector, right? That's the append for bus schedule. So we can make up a bus schedule by calling append. And the bus route also has an append function. Now, there's no relationship between this and that, by the way, but we like to call this append. So here we're essentially just adding a bus stop, which is a shared pointer. Okay, we're adding a bus stop to our vector, the member variable stops, so that you can make routes of many different stops. And then when you have the routes, then if you gather the trip info, and then you can make the schedule, right? So then you can make the stop objects by simply just making those objects with the constructors of this concrete bus stop types, right? The corner type and destination type, right? So I hope this makes it clear. That's why, as you see the advantage of a class diagram, this explains pretty much everything you need to know about the structure of your OOP program. And exactly these are all the things that we're dealing with. So then let's go back to the code. All right. So actually, let's start with the driver program, the test program that what we're actually doing here. Okay, kind of what I already kind of explained about the mechanism with that's fairly simple. So now first let's make a schedule, which is a object of bus schedule. And then we're gonna make a bunch of stops, right? So to make a stop, and just one little one important, I want something that's shared pointer here. Uh, we need to use the boost version of shared pointer instead of the standard version. So that because the boost version of shared pointer is the one that's serializable, and the standard one, so the boost has not added support for the standard smart pointers, but they have their own replacement smart pointers. They just work the same way. Yeah, even the naming are pretty much the same as the standard. Well, they are there because really they came out earlier than the standard had them, so that's kind of why. And so again, so use the you can use the function make shared to make a shared pointer, right? And this is with the boost domain here. Um, so we're passing in the GPS positions. That is really that's the constructor for a um, yeah, the bus stop corner, which we need to also initialize the base class, right? The base class holds on to these two values that you know pinpoints the location in terms of GPS, and and then of course this corner type bus stop has additional uh, information. That's the two street names. So we similarly we're gonna make a bunch of them. We'll make a bunch of a corner type, bunch of a destination type, and then we make a route. And so a route, we're gonna basically add those stops, a couple of different stops into route 0. And then we add those routes to the schedule now. So along with the trip info, we see the driver name and the hour and the minute. And then we'll make another route, which adds a bunch of other different, maybe some of them are shared. You see some of the stops are shared. We got a BS1 and here and a BS1 over there too, right? And then we'll have BS2 here and a BS2 over there. And then this has 3 and that has 0. So those are just different stops and some of them are shared. And indeed, that's why they are called a shared bus stop, right? So we're going to add those to a different route. So now we got 2 routes. And then we'll add this route to the schedule too. And we schedule the route. Now we got 3 different drivers, Bob, well, actually, the same driver, Bob, but different timing. That this driver drives on this route 0 at these different times. And we got Alice on this route, same route, but at 11:02, right? And then we'll have Ted on route 1 at 2 different times, and then we'll have Alice on route 1 at 11:47. And so then that's it. We made up all our objects, the whole bus schedule. We just we created a schedule, and then with the driver and their start time. And now we just print out the schedule. And now here we're calling this save schedule function, which is defined in the bus schedule. In fact, this in the bus schedule header there. And we'll look at that method in a minute. This is to save the schedule into a file. Now, this is for our testing purpose. We're still just dealing with our own local computer. We'll save it to a file. If you want to send it over the network to some other program, if you have another server that's running there, and then of course that works too, right? So this is for our demo purposes. So we're going to save it to a text file. And then maybe sometime later, then you're going to restore it, right? Let's say your program allows you to, pause and resume, right? That we don't have this thing built here, but you can easily build something like that, right? And then you load up that file and that preserve the state. And so when they restore the schedule, so instead of the data, just your memory, once the power is out and you lost it, right? So here we actually have this persistent that will save the state. And so now we can actually restore it from that file. So this just prints it out, and then you can do a comparison to see if they're the same, right? So that's the idea. That's the test program. And so if we look at the schedule and how did we save a schedule, right? Save a schedule. Now you got a schedule object, then you got a path to save to a file. And so last lecture we talked about the file system, basic I/O, right? So if you recall, now we're going to use OF stream to write to a file. It's an output file stream that stands for, and just use that standard library, which works really well. And here we're using a Boost library here. We're creating a text output archive. It's called archive. It's just kind of the terminology for serialized, uh, for the serialized uh, file, right? Serialized object is called the archive. So output archive, and now we're choosing just a textual format. So we're going to examine that file and see what's in it. Okay, assuming we're using the textual format, and there's also binary format you can support if you want. And then we'll essentially just save that schedule into this archive. And the archive basically, of course, just kind of redirects the content, the stream of bits into that file. Okay. And so now, of course, this object, this means when we've learned the operator overloading, this is the streaming insertion operator. That means we have overloaded this operator for this class to handle this operation here. Now, restoration is similar. It's now here, instead of an output archive, we have an input archive object, and then that's wrapped around a input file stream. That's when we read the file. And then to restore the schedule, first we'll make an empty schedule object, right? And then we're gonna just use the stream extraction operator. And then this is again overloaded on this iArchive class. So we're gonna, this operation will essentially use that mechanism that I was talking about, the concept of serializable. All those classes has the mechanism, and that's, essentially in those serialized functions that you define how each class is serialized or deserialized. So that's really this operation here. This is the meat where it's going to really do all this work to restore. And this is where it's doing all this operation to actually save, to serialize. This is the deserialization part of it. This is the serialize, right? This is a deserialize to restore your serialized data back into objects in memory, okay? All right, so that's really kind of the gist of that. And then let's take a look at a couple of different things. You can read more on this on your own. So let's take a look at, for example, now we have studied the inheritance and the polymorphism, and here this is a really good program. Actually, it shows you example how you might, it's just another example of a design that will talk about many of the idioms and the ways we talk about the how you control the the relationship between the derived and base classes, and the abstract class and how you implement those things. So let's take a look at like the stop. And I remember that inheritance hierarchy there. We got the stop and two different kinds of stops that derive from the bus stop. So bus stop here now, the actual constructor to construct a bus stop is now, this is a protector, so this can be uh, essentially this can be invoked from the derived classes, but there's no point for this to be invoked outside, because a bus stop is an abstract class. You cannot construct a object of abstract class. Now, but still, for the way that the serialization library works, you need to define a default constructor for all the classes that they are serializable. And there are alternatives. This is a simpler way, and the alternative way is you can. So here, see, there's a serialize function that's what makes it serializable. So the serialization library is going to look for this function. Here is actually a function template. So because this archive, could it be input archive, could it be output archive, could it be textual based or binary, whatever. They can be all supported here in this manner. And so for the serialization to work, so just kind of one way is to have a default constructor that may be used during the serialization, deserialization process. And then the other method would be you have uh, different kinds of serialization functions that will use your custom constructors if you want. But here, I think this is a simpler way to do it for our purpose. Now, so here, what we're doing here, so let's say you got an archive. Remember that I showed you how to save and restore, and you get passed in those archive objects. And here, these archive objects, they have overloaded this bitwise and the bitwise and operator. Again, here we're not doing the bitwise, but we use this as an overloaded uh, operator for this purpose. So here, and by the way, you can use the streaming insertion and extraction operator, but this really is combined. Say this function, it will handle both serialization, deserialization. So there's streaming insertion, streaming extraction, right? So if you, but then this ampersand, this bitwise and operator that's overloaded, this will be able to handle both direction. Okay, so this is why we're using this here. So again, of course, you can chain it, right? Just like the streaming insertion, um, the C out, and then you insert something and another something, right? So this is a similar concept. So we're essentially saying we serialize either, let's say we're doing the serialization process. That means we are serializing this latitude and then longitude, right? And then when we deserialize, right? Imagine this is the extraction, the other direction, and then we deserialize latitude and longitude, right? So it can go both ways, right? So that's a fairly decent way of doing the serialization, and it's now, of course, for the serialization to work, the serialization library needs to access your private member variables. How do you do that, right? You make a friend. So you make that access class from the serialization library, the Boost serialization library access class in a friend. So this is how you allow that serialization library to access your private member variables. Okay. All right. And that's really that I want to explain. And then let's look at the two kinds of stops. So here, this is way deriving from bus stop. We have a bus stop corner, and then this is the constructor here, and you see this is a calling the base class constructor that's protected. So you can uh, call that from the derived class. Okay, and what else here? So this is the overriding the pure virtual function description from the base class, and this is implementing it. And so we're simply implementing, okay, we're going to output street 1 and street 2. And so similarly, you see, you want to serialize um, the this derived class, and then we're going to first make that access class a friend, and then we implement a serialized function template. And here, there's a little difference here. We're going to serialize the base object. So this will handle the base object. Now, also we're using the ampersand, okay, the bitwise AND operator that can go both ways, depending on is it deserializing or serializing. And so we're going to serialize or deserialize the base object. Okay, and by providing, you provide a, basically you want to provide this object, okay, and then this object, and then using the serialization base object class, it will extract the base object portion of that. Okay, and then we have the additional member variables to serialize or deserialize, street 1, street 2. Okay, this is in a derived class what you do here. So that's that. Now we got the destination, which is the same thing. Let's see what else. Let's take a look at the route. Now the route, we'll also want to serialize that. And so we're going to also friend the access class and then implement a serialize function. That's the concept of serializable. Then the serialization library looks for this. So here, there's a bit of a different thing we need to do because we have a vector of a shared bus stop, and then we're actually using the pointer to base, pointing to base class, the polymorphic. So bus stop is a polymorphic class. So a little bit thing for the serialization library to know, we need to also register the pointer types of the derived classes. Now, there's a different way to register the derived classes, but this is just a simple way that I decided to use here. Again, you can just use this to register. Again, on the archive, there's a register type function you can call. And that's just the things that have to be done because this M stops, it's holding pointers to the bus stop is a pointer to base class, and in polymorphic at runtime, there could be the, one of the two kinds of actual bus stops, right? So the corner type or destination type. So this is just something that's necessary to let the serialization library know about the additional types, the derived types. And then same thing, you just serialize that vector, and the vector, it's supported uh, to be serializable as well. Of course, the standard library doesn't do that, right? So this is actually from Boost, and so you import this Boost version of a vector, and this has the serialization built in. So basically, all the standard library containers, they are supported. So if you whatever the container you're using in the standard library, you can still use that as is, and then but just so that when you import the booster version of the header, and that will make those standard library containers serializable. Okay, so that's that. So I think that's what I need to explain. There's let's see what else. Oh, let's run this thing. Okay. All right. So now you just after you, okay, let's take a look at the README. Actually, you need to do a reconfiguration first. By the way, the bus schedule, the class diagram source code is over there. You can go ahead and click into it and just look at. And then reconfiguration for Windows and a Mac, and now Windows. So remember previously you have made some symlinks to some of the Boost library modules for running the localization example. And so here we need to add one more thing. So we need to make one more symlink for the serialization module. So you just basically, first you go to that folder under the VCPKG. Remember that the VCPKG package manager that we installed, which we use that to install Boost on Windows, right? So essentially, you make another symlink, and then inside by the way, this needs the admin privileges, okay? So you open a separate PowerShell terminal, and then once that is done, and then you just do a bdep init, and with this additional piece that will initialize with this serialization library. And then you can build and run, okay, once you've done that. Now, if you're on Mac, essentially that's the only command you need to run. You run the bdep init. And then the build and run, so essentially same thing for Mac and Windows. Okay, so I think I have built this, then I'm gonna build this one more time. Okay, up to date, so it really didn't do anything, it's fine. So this is the symlink to the program. and you run this. Okay, so so this is the schedule. You have the time with the driver's name. That's the trip info, remember, and then you have um, the route information, and here it actually prints out the it prints out the address, the memory location, so that you can compare if those objects are at the same location, if they actually are pointed to shared, let's say a shared bus stop, let's say the White House, for example, 05F90, right? This one, you see the White House, same memory location, okay? Same memory location wherever this appears, because they are shared pointer to the same object. There's only one copy. Now we'll print out the address because when we restore, we want to see how many copies of the White House object we make, right? The bus stop at White House. And so it should expect it should be just one copy as well. So even though it appears at different routes, so that is what it should be. And it will also print out the GPS location as you see. All right. So we'll print out basically all the trip info with the route. Now remember, this is a trip info with one route. This route has 3 stops. And then we got another trip info. This is like an entry of the schedule, right? So, and so on. And then that was written to a file, a temporary file in this path. Now your path on Windows will be different. And that will be printed out as well. You can examine that file. So we're going to take a look at that file in a second. So it will restore from that. And this is the line where we're looking at this program here. So where we're doing this restoration here, right here. Okay, so that all this data was serialized at this point into that file, and now we're gonna deserialize from that file. So same, you can compare. Is the same kind of data. Of course, the memory location will be different, right? When you um, essentially create a new object from that, and that's what really is happening. And then if you compare the White House like this, 6DD0, 6DD0, and wherever the White House occurs, you see the same address. That means it's still a shared pointer that's restored properly, okay? So that's it. That's what I wanted to share about serialization, deserialization, or SIR, DSIR for short. Thank you.